All right, well, good evening and welcome to lecture number 2 for MT225. Last time we got ourselves established a little bit, I introduced you to the basic principles of mechanics. And tonight we're going to lay the groundwork for most of the work we're going to do this semester. We're going to need to make sure we've got some mathematical skills prepared. Most of what we do tonight should be review for everyone. Pretty much everyone here has gone through my math class in the A&P program, and we cover pretty much every concept. There's a couple little bits that are different, but you've at least seen most of it before. So at most, it should be a review. It's not going to be a whole lot of new material tonight. Uh, on Wednesday night, we'll be getting into a little bit of algebra you may not have been familiar with, but we'll look at how that works and work through that. But tonight's going to be all about just getting the basics down, making sure we're comfortable with all the fundamental skills we'll need for the semester. So some administrative details. Like I mentioned last time, I wanted to make sure that was documented here in the notes, so everyone who's seeing us live or who check out the video later will be aware of this. That the class time, we're just going to shift by 10 minutes compared to the official schedule. The official schedule has us starting at 5:10. We'll just start at 5. That way, we're done at 7:30 instead of 7:40, and the practicum boundaries will be about the same. We'll do usually 5 to 6, 6:15, 6:20 or so on the lecture, and then the rest of the time is practicum after a few minutes of break. If anyone still has to add the class, the data is right there. At least one, maybe two people still need to fill out their paperwork on that. You definitely want to get that done this week. If you wait until next week, I think extra signatures have to be put on the ad form. So make sure you get that ad form in. No, there's all our contacts here. We have our class website where you can get all the class notes and materials, our YouTube channel where you can find these videos. So if you need to go back and review anything or see any of the practice problems we do, there we've got the YouTube channel set up for that, and our Zoom meeting, which as long as we need it, is not going to be changing. All right, so our main objective tonight, we're going to take a look at the basic math that we need. Not quite as simple as where we start in the A&P program, but a little bit of review of the basics of numbers and units and unit conversion. We'll take a look at scientific notation and review what that is. We'll talk a little bit about precision and accuracy. This is an engineering course, and one of the things that we have to be careful of is controlling round off error, is making sure that we have enough quality in our measurements and our information that we use in our calculations so that at the end of the problem or at the end of the design, whatever we're working on, we haven't introduced error due to rounding numbers off. In the A&P program, we sort of treated that kind of arbitrarily. We just said, well, if you keep a certain number of digits, you're going to be fine. But we have to have a little more control over that here in an engineering course. So we'll talk a little bit about that. So we'll look at significant figures in the context of precision and accuracy. And then we'll do a little bit of algebra review, just basically the fundamentals of solving equations. So I'll put a few practice equations up and we'll work through those so you get the basics down. You'll be spending a lot of time solving equations similar to the ones that we'll be working with tonight. The big difference between the equations we'll work with tonight and the ones you'll be solving in real problems is the numbers are not as nice in the real problems. In the sample problems, it's common to get nice whole number answers with whole number coefficients and all of that. Reality is rarely so kind. So we end up with lots of ugly numbers that we end up having to do work with. So, but the basic skill is the same. So let's go ahead and take a look at the basics. So numbers. Remember what numbers are all about. We use numbers to describe quantities and to manipulate those quantities through operations. So, our common operations, addition, subtraction, multiplication, division, powers, roots, other operations that we'll see, uh, these operations all represent something physical. And that's the big thing to keep in mind, especially in an engineering class, is that everything's got to be physical. The whole point of the class is to essentially learn how to design uh, structures. And it's not going to be a good result if we have an answer that is unphysical. We need to have answers that are physically meaningful. So every operation we do has to be physically meaningful. So we have our operations, addition, subtraction, multiplication, and division. And we'll be spending a fair bit of time with those in practical applications. We don't tend to see a lot in the way of powers and roots. Nature doesn't tend to involve powers and roots too much when it comes to things like forces. There are a couple places where it comes in. The Pythagorean theorem is something that we're going to revisit on Wednesday, and there's definitely powers and roots involved there. But for the most part, we'll be spending most of our time doing addition, subtraction, multiplication, and division. I should say it's your calculator that's going to spend most of the time doing that. We don't spend a lot of time doing calculations by hand. So, just a little bit on numbers to hit the objective in the course outline. Uh, most numbers that represent a count or that represent a ratio, those numbers are dimensionless, and we call them pure numbers. Pure numbers don't have units associated with them. They don't represent physical measurements. They represent comparisons in a ratio or just a count, how many students are in the room, for example. So a pure number or a dimensionless number gives us enough information with just the number itself. If I say there are 5 students logged in here, then we know immediately how many we've got. We don't have to have any extra units, or a total of 6 people. We don't really need to add units in there. So it's usually just a count or a ratio. We don't run into too many pure numbers in the practical aspects of this class. Uh, Most everything we deal with is some sort of physical measurement. So our numbers are dimensional. They have some sort of physical size to them. And to provide an adequate description of that number, we need a unit. So it has 2 parts: the number, and then what the fundamental reference is, what the size is. And so this is, again, something that should be relatively familiar, especially for those of you who just went through the first semester. Uh, we dealt a lot with units and measurements. Everything you calculated, for the most part, had units on it. So let's go and take a look at units. Dimensions and units, this is basically copied right out of the AMP program slides, but as a review for everyone, dimension is just sort of a fancy way of describing the type of measurement that we're making. So the way I like to think about dimension is based on the tool that I'd use to make the measurement. So for example, if I'm going to measure length, I'm probably going to pick something like a ruler or a tape measure. I'm not going to be able to measure time as easily with a tape measure. I'm not going to be able to measure temperature with a clock. If you have to use a different tool to make the measurement, chances are it's a different dimension. So dimension is a fundamental type of measurement, or a fundamental type of way of measuring something. And there aren't that many of those fundamentally. I believe there are only about 7 that people recognize as being fundamental units of measurement. Everything else is kind of a combination. For example, speed is a combination of distance and time. Distance and time being 2 fundamental dimensions. So we have a few examples there that we've encountered, things like mass, how much material something is made up of, length, how far it is between 2 points, time, pressure. which we deal with a lot in the A&P program. We'll deal a little bit with pressure here. We'll find out that there are internal forces in materials that we call stresses that are effectively just pressures. Forces, we'll be spending a lot of time with forces, and not so much with temperature or frequency, but those are others that come up in different applications. Then we've got the unit. Units are our reference. They're our comparison. They're what we're expressing our measurement in terms of. So when we measure time, for example, we need some reference to be able to tell us, well, how long is it from this time to the next? And that reference can vary. Just thinking about time, we've got several different measurements that we could use for it. We could use seconds, we could use minutes, we could use hours, days, weeks, months, years. All of those are measuring the same fundamental quantity. They're still measuring time, but they're measuring different amounts of time. We're grouping together different amounts of time and calling it by a different name. So that's kind of a good way to think about units. Units are names for a reference, for some fundamental or some size comparison that we're doing. So it's a reference measurement for a particular quantity. And so some examples here, we could measure things like mass or weight in pounds. Length could be miles. Length is one of those that has dozens and dozens of different kinds of units associated with it. Time, pressure, we know what pascals we don't use too much, but in aircraft maintenance, but we do in structures when we're dealing with metric. We're more familiar with PSI, pounds per square inch. That's a perfectly fine unit of pressure, and we'll meet a couple other variations of that as we get a little further in. Newtons and pounds for force, Kelvin for temperature, all sorts of different units out there. There are thousands and thousands of different units out there. There are only a handful of different types of measurements that we can do. So out of that issue with units, we run into a couple problems. Because there are so many different units, confusion can be a big issue. Lack of communication can be a big issue. So if I'm talking about a measurement in inches and somebody else is talking about a measurement in feet, we may not be communicating, and we could end up causing a lot of problems. And we've all seen examples of that. I showed the Gimli glider video in class where confusion about the measurement of fuel quantity was led to a situation where the aircraft took off with half the fuel it needed to get to its destination. There have been many different issues with that in the past. So it's something that we've learned as a society we've got to pay really close attention to, or it's going to bite us. So we will be using both metric and standard units. We'll be leaning a little more on standard since that's what everyone here is a little more familiar with. But we will have a few problems involving metric. But as it was in the A&P program, official course policy is that if a number needs units, which pretty much every number we deal with is going to have units on it, and you don't have those units there, the number's meaningless. And that means it's not communicating the information it needs to communicate. So answers given without units are incorrect. They are wrong. The only time that we can get away with it is when we have a ratio that we're dealing with. And there are a few cases where we'll be dealing with ratios where you can get away without writing a unit. But the majority of the time, we're going to be needing units on our answers. So make sure you present those. Now, when I was in engineering school, it was a much more harsh environment with respect to units. You could do the entire problem correctly, and it could be 2 or 3 pages of write-up to try to get to the right answer. You could have done the entire problem correctly. If you wrote your answer down without units, you'd get 0 credit. I'm not that harsh here in this kind of class, but there will definitely be some point loss if there aren't units on the answer. And that's done to encourage you to pay very close attention to those because it is a communication issue. Now, practically, the biggest issue we have with units is converting from one unit to another. And that's one of the first kind of practical skills we're going to work on tonight. Um, some of the units that we'll be dealing with this semester, we've got force, which we'll be mostly measuring in pounds. Newtons we'll see occasionally. And then we've got one that you may not be familiar with. We've got what's called a kip. Kips are a bit of a strange combination of units. Um, it's one of these situations where we've combined together a standard unit and a metric prefix. And I've talked to most of you before about situations where that comes up, where we, for example, for sheeting, for plastic sheeting, we use mils. A mil is a milli-inch, a thousandth of an inch. This is a case where the normal unit, the pound, is really kind of too small for what we normally would use. In structures, it's not uncommon to be dealing with thousands, tens of thousands, even hundreds of thousands of pounds of force. And writing all those zeros gets tiring. After a while, you can make errors dropping a zero and so on. So we shift our units over into units of thousands of pounds, or a kilopound. A kilopound is a kip. So a kip or kips is, when we say 5 kips, we're talking about 5,000 pounds. It's just an easier number to deal with. So that'll be one that we'll use occasionally, and we'll use fairly frequently. We have moment. Now, everyone here should be familiar with moment from what we've done in things like weight and balance. Well, moment comes back here too. And working with structures can have twisting loads on them, have turning loads on them. Those are moments. And those moments are going to be a very important part of certain systems. When we deal with moments, we've got any combination of force and distance. Remember that a moment is a force applied some distance away from a pivot point. Well, that distance could be in inches or feet, could be in meters. The force could be in pounds, it could be in newtons, it could be in kips. So a kip foot, for example, is a perfectly fine unit of moment. It's a big unit of moment. It's 1,000 foot-pounds, but it's a large amount of moment. It's a perfectly valid unit. We sometimes see inch pounds, but since we're dealing with structural loads generally tend to be pretty big. So foot pounds, kips feet, newton meters, very common units for moment. Then when we get into our strength of materials portion of the class, we're going to be taking a look at stresses and pressures. Stresses are measured in units of pressure. And so we have things like PSI, pascals you may be familiar with, and kilopascals as units of pressure. The two that are in there that you might not be too familiar with are KSI and MSI. Well, again, we're following the sort of strange tradition of mixing together metric prefixes and standard units. A KSI is 1,000 PSI, and an MSI is a million PSI. We have thousands for kilo and millions for mega. So KSI and MSI come up when we deal with structural loading and stresses. And then as far as things like mass go, for our purpose in the standard system, we can use pounds. We don't have to worry about the issues with mass versus weight in the metrics in the standard system. In the metric system, kilograms are perfectly fine for mass. If we need a force out of that, we'll figure out how to get it. So those are the pretty common units that we'll deal with. But the big skill that we have to make sure we're familiar with before we get into any other kinds of calculation is figuring out how to convert from one unit to another and being able to do that reliably. In fact, it's one of the major objectives of this course to make sure that you know how to convert from one unit to another. And I'll review with you here the method that we used in the first semester, and we'll do some examples to remind you of how to work with that. The thing to keep in mind is that we have some pretty strange units that show up in the field of engineering. You can't always be guaranteed to find a conversion factor. You can't always go to Google and say, hey, take this unit and turn it into this other one. It might not know how to do it. But the method I'll show you, if you know how to convert each individual piece, you can handle any unit that you'd ever run across. And so we'll see how to do that. So as long as two units measure the same dimension, we can convert between them. If we have two measurements of time, something in hours and something in minutes, we could convert between those. Minutes measure time, hours measure time. If we're looking at distances, we look at feet and inches. Both measure distances, so we can make conversion between them. We can't easily convert, or I should say reliably convert between things like distance and time. Although we do that kind of in a everyday language sort of sense. When we ask how far away something is, oh, it's about an hour. We're using a lot of extra information to try to make that, and a lot of assumptions to try to make that kind of statement. We can't be that lax in dealing with engineering. So we have to make sure that we're always converting between two units of the same dimension. So let's try some examples here. Let's start with a little bit simpler one here than going between miles and kilometers. Let's go over to the whiteboard here, and we'll see how that works. Let's see, there we go. I guess I've got to stop the screen share. There we are. And oops. All right, stand by 1 second. Just getting my screen set up here. I'm trying to remember how I did this last semester. All right. Let's try that. All right, there we go. So everyone should be able to see the table here, see the white surface, just some scrap paper on my desk here. So let's see how we can convert between a couple different units. So let's start off really easy with something that everyone's probably familiar with. We'll start off with inches and feet. Pretty common conversion, one that we run into all the time. It's not uncommon in a specification, for example, to be dealing with a beam that is a certain number of feet long, and then some sort of feature on that beam, some number of inches in from one end. So we have some information that's been given to us in different units, and we'd have to convert those to be consistent. One of the biggest mistakes we can make is to try to add or subtract or to multiply to work with any kind of calculation where we're trying to combine something in feet and something in inches. If the two numbers are not in the same units, we can't combine them. Now, the fundamental thing that we need to know, fundamental piece of information we need when we do any kind of unit conversion, is we need to have the connection between those. And I always like to write it as an equation. If I think about feet and inches, the easiest way for me to describe the connection between feet and inches is to say that 1 foot is equal to 12 inches. I always like to take one of whatever the bigger unit is and then express that in some count of the smaller unit. So 1 foot is 12 inches. Now you can flip that around and you can figure out a relationship that says 1 inch is some number of feet. It's going to be some small decimal number. It's actually 0.08333, something like that. There are a lot of issues with that. If you can stay with these equations, conversion equations or conversion factors that involve whole numbers, you'll end up with more accurate results because you haven't introduced round off error into the situation. And I'll show you here by this method that that I tend to use for converting units. All you need is this connection. You don't need to use a different equation if you're going from inches to feet than if you were going from feet to inches. It all works the same way off of the same conversion factor. So let's take as an example here, let's say we have a distance of 16 and a half feet. So we have 16.5 feet. We want to find out how many inches that is. Well, first think about what your answer should be. One of the big items to take away from a class like this, since everything we do is practical, everything we do is a realistic solution, then there should be some way to reason about it, to be able to predict it, or at the very least ensure that that our answers are reasonable. Because if our numbers come out unreasonable, if they're not something that could physically be correct, then we've definitely screwed something up. So when you're working with units, think about the direction you're converting in. If you're converting from a bigger unit to a smaller unit, like we're doing here, we're converting from feet to inches. An inch is a smaller unit. So to measure that same distance of 16 and a half feet, if I had a block that was an inch long, I'd need to lay a lot more of that block against each other. You have to stack them all up quite a bit in order to reach that 16.5 feet. So I should expect way more than 16.5 inches. If you're just blindly plugging numbers together and multiplying and dividing with no real clue of what you're doing, you can pretty easily get an incorrect answer here and end up with a smaller number of inches representing this measurement of feet. That can't be reasonable. It can't be correct. It won't make sense. So the advantage here of the method that I'll show you is that as long as you set it up correctly, it'll always give you the right answer. But you should always rely on that physical intuition or that mathematical intuition to predict your answer. Figure out the size of your answer before you start. So here I'm expecting some large number of inches, something a good bit bigger than 16.5. If I get something else, then I know I did something wrong. Now, the method that I use here, I refer to it as the box method. And it's called that because you basically draw a couple lines on the page, dividing things up into different boxes. Now, the number that you're starting with goes in the upper left box. Down here, the lower left box, we're not going to do anything with right away. And so I'm just going to put a 1 there because what we're really doing is building fractions. And if I had this on my whiteboard, when I'm done with it, I'd erase the bar in the middle and we'd have 2 fractions that we'd be working with. So what we've really got here is 16.5 feet over 1. These other 2 boxes, these are going to take different sides of our equation. We have to pick one side or the other and put it in the top, and then use the other side in the bottom. Which one goes where depends on what we're trying to convert. Here we've got feet, and we want to get rid of feet. We want to cancel out that feet in favor of inches. And since feet is in the top, to cancel it out, we got to put something with feet in the bottom. And the only piece that we have that has feet in it is the 1 foot. So I'm going to take that piece and I'm going to put it right in here and say 1 foot. All I've got left is that 12 inches, and that's what's got to go in the other box. So one side, we can always figure out where one side of the equation goes, and that'll lock down what we have to put in the other side. So in the other box, so 12 inches goes there. So we're always just splitting up this equation. One side goes on the top, one side goes on the bottom, and you figure out which is which based on what you want to cancel out. If you've set it up properly, then you should be able to cross out the feet. You got 1 copy of feet in the top, you got 1 copy of feet in the bottom. Now this really is just 2 fractions, and I'll go ahead and eliminate the bar there in the middle. It's two fractions. It's 16.5 over 1 times 12 inches over 1. So let me write that down here. I'll write it as 16.5 over 1 times 12 inches over 1. And if you remember a little bit about multiplying fractions, when you multiply fractions, you multiply across the top and you multiply across the bottom. So across the top here, I've got 16.5 times 12, and that inches just rides along. And underneath, we just got 1. So we can come up with a number here on that. If we multiply 16.5 times 12, we get 198 inches. So that's a reasonable result. That's a reasonable value. It's bigger than 16.5. So it takes 198 inches to span the same distance as 16 and a half feet. So that's going from feet to inches. Now, if you go and look up in a table somewhere, if you're used to doing that, a lot of those tables are written out by saying if you have feet, you'd multiply it by 12 to get inches. And that's correct. That'd work out just fine. Where sometimes errors come in is when you use that same kind of technique, you go the other way. When you do that, if you do it by multiplication, you end up rounding things off a little bit too much. So this method is actually, it will give you better results no matter what way you're converting, because it doesn't rely on round off error that's already been introduced in a table. So for example, here, you might go and look up in a table like the one we have in the mechanics handbook. It says if you have feet, multiply feet by 12 to get inches. But then it'll also say, well, if you've got inches, multiply it by 0.083, and that'll give you feet. And while technically that's correct, this has lost a lot of information here. 0.083 is not 1 over 12. It's close, but it's not quite 1 over 12. And we'll see a little bit later this evening that we've lost quite a lot of information here. And it means our answer is going to be a little bit off. And that means everything we calculate from that answer is going to be a little bit further off. And we end up with problems down the line. So the method that I'm showing you here works better. So let's see how that gives us a better answer. So let's take a distance of let's say 260 inches, and we want to find out how many feet that is. Well, we can use the same equation. All we ever need is one connection between feet and inches. 1 foot is 12 inches. That's all you ever have to remember if you need to convert from one to the other. So let's set up our boxes. We can put a 1 there in the lower left. We'll have 260 in the upper left. Then we have to pick which side goes where. Well, I've got inches in the top, so I need something with inches in the bottom. So I'll take the side of my equation with inches in it. That's the 12-inch side. I'll put that in the bottom. I've got to put something that 12 inches is equal to on the top, so that'd be the other side of the equation, 1 feet or 1 foot. If we've got that set up, the inches cancel out, and all I'm left with as far as units go are the units that I want. I wanted feet. Now, if we multiply this across, 260 times 1 foot is 260 feet. 1 times 12 is 12. Well, we can divide that out. 260 divided by 12. There we get 21.666666 going on basically forever. Feet. Now, realistically, we'd never let the answer go on forever. There is some point where we can stop writing a repeating digit, and we'll see exactly where that is when we look at significant figures. Let's compare that here to the result we would have gotten if we just multiplied by 0.083. If we took 260 times 0.083, we get 21.58. That'd be inches to feet. It doesn't seem like it's off by that much. 21.66, 21.58 doesn't seem like too much, but there's enough off there that if we plug that into other calculations, that it's going to throw those even further off. And then after enough cascading of this round off error, we suddenly have an answer that's nowhere near the right value. So you got to watch out for that kind of thing. If you're used to using tables and such, it's not always clear where they've rounded off. And those tables, those conversion tables and such, some of them are pretty bad. It's always better to go with these nice, simple whole number equations, or to a better resource, something that you know something about how many significant figures they're keeping in their round off. So that's converting feet to inches and inches to feet. Let's take a look at some of the other examples here. In the notes, we have kilometers per hour to miles per hour. So that's a little bit more sophisticated one, and I'll show you what you do with that other box on the left. So let's say we have let's say 90 kilometers per hour, and we want to know how many miles per hour that is. So we want to convert that to miles per hour. Well, if you break down miles per hour, that is a mile per hour. Remember what per means, by the way. Per means division. So we have 90 kilometers per hour, and we want to find out how many miles per hour that is. Well, to do that, all we're going to have to do is convert the kilometers and the miles. The hours are the same, so we really don't have to do anything to the hours. So if I set that up in a box, this is where that bottom box comes in here. Whenever you've got a fraction in your unit, you can put the denominator of that fraction in the bottom box. So this is 90 kilometers in 1 hour. Some people like to even just write the 1 hour specifically in there. It's 90 kilometers per 1 hour. We need to figure out a relationship between kilometers and miles. And for that, you can go to pretty much any resource. I have a little software package I use on my laptop called Units that just lets me type in 1 unit. It tells me the conversion factor, conversion equation. So let's say I have 1 mile and I want kilometers. So this will give me a good relationship between miles and kilometers. 1 mile is 1.609344. So that's got plenty of digits to it. No round off issues that I'd be worried about there. Kilometers. So a mile, a little bit more. Well, more than about a mile and a half, more than a kilometer and a half. So it's a 1.6 kilometers for one mile. So let's go ahead and convert that. We need to plug in something in kilometers to cancel out the 90 kilometers. So that'll be the right-hand side here. We'll put in the 1.609344 kilometers. And then put the other side 1 mile. If we've got it set up right, the kilometers will cancel, and we'll be just left with miles in the numerator and hours in the denominator. Remember, we're dealing with just fractions here, so we multiply across the top and the bottom. So we have 90 times 1 mile, that's 90 miles. Then we have 1 hour times 1.609344. That would be 1.609344 hours. And we just divide that out. So now we can run over to our calculator. 90 divided by 1.609344. And we get 55.9234. And that goes on. We'll do 0.7. There we go. And don't forget the units on your answer. That'll be miles per hour. Now, it can be kind of hard with units like this that are combined together to really figure out whether or not your answer is going to be bigger or smaller. You may not have enough familiarity with the units involved to be able to say, yeah, I know this is going to be a bigger number or a smaller number coming out. But as long as you lean on this method to get your pieces in the right places, you have a pretty high probability of getting the right value out. And then you can check it on the backside of it, make sure that it makes sense. Well, I know that miles are longer than kilometers. So if I've got a speed in kilometers per hour, I'm probably not going to need as many miles per hour for that. So miles per hour, same speed is going to have a smaller number with it. Bigger unit, smaller number. So that's an example there. Let's do one other example. I think we're going to go off of the script here, I suppose, because the other two examples are pretty straightforward ones. Once you figure out the connection between those, then there's really not a lot to do. It's just like the feet to inches kind of conversion. One that I find trips people up a lot is when you've got powers involved in the unit. So let's take something that we're feeling relatively comfortable with, like feet and inches, and look at something like area, feet squared or inches squared. So let's take, say we've got an area of 25 square feet, and I want to find out how many square inches there is. Now, the big mistake I typically see people make with this, and I even see people at a lot higher levels in graduate schools and things like that making this kind of error, just going too fast and not paying attention to what they're doing. They see feet and inches and they think 12, and they multiply or divide by 12, and that doesn't get them the right answer. If you follow it through with the box method, it will work out correctly. So let's see what we can do here. So we've got 25 square feet. Now remember what square means. Square means two copies multiplied together. So this is really feet times feet. And the square is only on the feet. It's not on the 25. The 25 is sitting out in front. There aren't parentheses here making the squared see the 25. So we've got 25 square feet. We know our connection between feet and inches. 1 foot is 12 inches. Now, if we plug that in to our box, we can certainly do that. We got feet in the top, so we need the foot side in the bottom. I can put a 1 there. And then we'd put 12 inches on the top. Now, the problem with multiplying this through right now is if you're not careful, you might not notice that your units that you're trying to get rid of haven't completely canceled out. I've got 1 copy of foot in the bottom, but I've got 2 in the top. If I cancel those out, I'm only going to lose 1 copy. I'm still going to have feet in the top. I'm not going to lose both copies of feet. So how do we handle that? Well, the box method's pretty flexible. We can just add another column to our box method. If we need to add more conversions and we want to do them all in one step, we just have to keep on adding columns. So we can do this again. We can use 1 foot and 12 inches again. Now I've got 2 copies of feet. I've got feet times feet in the bottom. That's feet squared. And I've got feet squared in the top. They cancel out. And all I've got left are inches and inches. So watch what happens when this multiplies across. We've got 25 times 12 times 12 inches times inches. Well, inches times inches is square inches. So our unit that we wanted has fallen right out. We can calculate the rest. The rest is just working with numbers, and that's 3,600 square inches. So be careful with that. When you've got powers on your units and you have to convert the unit that has the power on it, be careful. It's the kind of thing that can be tricky. Lay it out very carefully. Make sure things cancel out and you'll never go wrong. Try to do it fast. That's when I start seeing errors and I see people telling me, well, this is 300 square inches. Well, no, it can't be 300 square inches. There are 144 square inches in a square foot, and I've got 25 of these things, so it's going to be a much larger number. Any questions on unit conversion? That's one of those areas I do see people getting tied up in occasionally. So you want to make sure you're feeling comfortable with it. And on our homework assignment that'll be issued on Wednesday, you have some practice on converting units. So let's go back over to the notes here. There we are. So there are a couple other examples of unit conversions that you can work on your own. There are grams and kilograms and pounds and newtons. You just have to look up the right values there. Kilograms and grams shouldn't be too difficult because of metric prefixes. And I've listed the metric prefixes in here that you should all be pretty familiar with at this point. Just with for those of you in the second semester now, you spent a good bit of time last semester working with electricity and got pretty familiar with your metric prefixes. So these shouldn't be unfamiliar to you at this point. Kilo and mega are typically the ones we use the most on the large side. We don't really tend to spend a lot of time on the small side in structures, in dealing with structural engineering. So kilo and mega, as long as you're familiar with those, you should be fine with most everything. You'll get a little practice with metric prefixes, get a chance to review on those when you work with your homework assignment as well. But I think everyone's feeling pretty comfortable with those for the most part, so I'll leave that to you to practice with on your homework. Let's take a look at scientific notation. Now, scientific notation is something we use when we deal with numbers that are either very, very large or very, very small. And again, something that you've gotten some experience working with things like electricity. It's just a shorthand. It's a way of writing out a number so that we can write it more compactly. It also has some other advantages that we'll see here this evening. But for the most part, it's just a way to write a number more compactly and to be able to get that number into or out of your calculator more easily. So we use the fact that powers of 10 move decimal points around. Every time we multiply by 10, the decimal gets dragged to the right. And every time we divide by 10, it gets dragged to the left. So we write a number as a product of some number between 1 and 10 and a power of 10. The power of 10 tells us where the decimal point really belongs. When we write a number between 1 and 10, the decimal is always in the same place. It's after the whole number, but before the fractional part. So the decimal's there. The power of 10 moves it to where it needs to be. So for example here, very simple example, we've got 121. 121 is the same as 1.2 times 10 to the second. So let's see, how is that? Well, let's see how that works out. Let's go to, if I have 1.21 times 10 to the second, the power of 10 always tells me how to move the decimal point. So my decimal point's right here in between the 1 and the 2. The power of 10 is 2. Positive powers of 10 move the decimal to the right. Negative powers of 10 move it to the left. So 1.21 with the decimal moved 2 places to the right, that's 121. And you'd use the same process to take a number that is in the full format here and write it as a number in scientific notation. Let's take, for example, a small number here. Let's say 0.0135. Well, to write this number in scientific notation, we'd need this to look like a number between 1 and 10. So we'd drop our decimal point between the 1 and the 3. But the decimal needs to be 2 spaces to the left. So we need to put our instruction here in the power of 10 that shifts the decimal 2 places to the left. That's going to be a -2. So 1.35 times 10 to the negative second, that's saying take 1.35 and move the decimal 2 spaces to the left. Remember that positive powers of 10 go with big numbers and negative powers of 10 go with small numbers. If you get confused turning a number into scientific notation or taking it out, if you remember that basic fact, you'll be able to figure out and not be confused. The positive powers of 10 go with big numbers. Negative powers of 10 go with small numbers. So there should be another example. There's another example right there. 0.0031. That's 3.1 times 10 to the negative third. If you start with 3.1 and shift the decimal 3 places to the left, you've got 0.0031, and that's a small number. So it goes with a negative power of 10. All right, so any questions so far? All right, then I'll assume the silence to be confirmation that there are no questions. So let's take a look at something a little more engineering related, precision and accuracy. If you had tools and measurement with me, we talked about precision and accuracy quite a bit. Precision and accuracy are two terms we tend to use interchangeably in everyday language, but they mean different things. Precision is really all about the tool that you're using to make your measurements. So precision is about the finest division on the tool that you're using. So for example, if you've got a ruler that has marks that are 1/32 inch apart and they don't get any closer than that, then you've got a tool with a precision of 1/32 of an inch. If you've got a gauge on a flight deck that has pressure marked off in 5 psi increments, you've got a gauge that has a 5 psi precision. We see this all the time on working with jet engines, EGT. Usually the gauges are 20-degree or 50-degree Celsius EGT gauges, depending on which kind they are. Usually the 20-degree type are what we see for starting things like APUs and such. 20 degrees is the smallest increment, so that's the precision of the instrument. So precision is about the tool. The precision is set when the tool is made. You can't change the precision. You can't go in and make new marks on the tool for the most part. So you can't really change the precision of a tool. Accuracy, on the other hand, is about correctness. Accuracy is about how close our measurement is, no matter what tool we're using, how close our measurement is to the right answer. Now, unfortunately, reality doesn't come with an answer book. So we don't know what the right answer is for the most part, but we do know that when we use a tool, the most we should be off, if we're using that tool correctly, the most we should ever be off is 1 division. You might read it a little high, you might read it a little low, but if the divisions are there, you're not going to be off by more than one division. So if you're reading a ruler that's marked off in 30 seconds, you might be 1/32 high, you might be 1/32 low. We tend to try to replace accuracy with precision because we figure that if we're using very highly precise tools where those divisions are so close together, then the amount that we can be off is very small. Now that makes an assumption. It makes an assumption that the tool is working correctly. And if the tool isn't working correctly, say for example, a micrometer that's been damaged, it may produce a highly precise reading down to the thousandths or 10 thousandths of an inch, but that reading might not be connected at all to reality. So accuracy is how close the measured value is to the true value. And it relies on both proper use of tools and calibration of those tools, making sure that those tools are giving you correct and accurate results. Now, this is the part that's a little bit different than what we've dealt with in the A&P program. This is really where significant figures come in. When we write a number down, what we're really doing is describing either a measurement or a number that's been calculated from measurements. In reality, everything that we do is a measurement, and then we calculate based on those measurements. When a number is written down, we're making a statement about the precision to which that number was measured. So if I write down a number with lots and lots of digits after the decimal point, if that number is a measurement, the assumption by anyone reading that is that this person used a very highly precise tool to be able to make that measurement. So for example here, if we say are using our measuring tools and we make a length measurement of 0.1236 inches. Well, that's not unreasonable for a micrometer. Vernier micrometer could do that down to the 10,000th of an inch place. So it wouldn't be an unreasonable assumption if I wrote down that number or saw that number written down. Physically, yeah, somebody could have measured that, and it wouldn't be too hard. A relatively cheap measurement tool can do that. On the other hand, somebody says they measured, let's say, 0.123579864 inches. There they have measured out to, well, let's see, we've got a very high degree of precision here, well past the millionths place. And millionths is right here. So we've got billionths, we've got a very, very high degree of precision. We don't have measurement tools, at least not measurement tools that are commonly accessible and available to make measurements down to that precision. We can get to here pretty easily with more expense than a vernier micrometer, but we can get there. We can get down to here with some pretty significant difficulty, and then the cost just keeps going up exponentially for each and every additional digit in that tool to be able to measure to that kind of precision. So it would be unreasonable to assume that this was an actual measurement. Now, in engineering, we don't want there to be confusion about the sources of our numbers or the way those numbers were measured. So when we write a number down, we've got to be aware of how it was measured and what precision we can really trust it to. If I had this number written down, given no other information about it, and other than that, I know it's a physical measurement that somebody took, I'm probably not really going to trust this thing past maybe the first few digits, maybe only the first couple, if I don't really know what tool they used. So there's an inherent statement in the way we write a number about how that number was measured, and we have to be aware of that, and we have to control that in many of the calculations we do, because it's not impossible to have this come out as a calculation. If you took a square root of something, if you used different methods of calculation, you could end up producing way more digits than are really reasonable. And that's what we're going to see in our next example here. So this is where significant figures come in. Now, I introduced significant figures to you in the A&P program mainly as a way to know where to round off, where you were given some instruction about where you should round off and how you should count the digits up to figure out where you round off. So first, a little reminder of how to count significant figures. For the most part, pretty straightforward. It gets a little tricky when zeros are involved. If you've got a number with no zeros in it, figuring out the significant figures is pretty easy. You start from the left. You always start from the most valuable part of the number. That's always on the left. So you write down the number of, or you count up the number of significant digits from the left to the right, and you keep on counting until you get to the end of the number. And there are some cases where we have to make some special counts for zeros or stop counting, depending on different things. But we'll see that in some examples. But the number of digits we write does make a statement. A significant figure, what a significant figure, a significant digit really is part of that number that we believe to be accurate. It's really about accuracy. What's real and what's just noise? What's representing the measurements or the calculations we're making, and what just comes out because we've done calculations and we've got operations that produce extra digits. So a significant figure is one that's thought to be accurate, and the results of calculations can produce more significant digits than we had in the originals. This especially happens with things like angles. We might only measure an angle down to 1/10 of a degree. But when you take a sine or a cosine or a tangent of that angle, you're going to get a whole lot more digits. And some of those digits are significant, some aren't. And I'll show you how to figure out which ones are significant and which ones aren't. So we've got to know how to count significant figures first. And here's where the procedure is written out in the notes. You start at the left with the first non-zero digit. That becomes important in really small numbers with lots and lots of leading zeros. We only start with the first non-zero digit. And we count left to right across the number. We stop counting at the last non-zero digit unless we have trailing zeros to the right of the decimal point. So this is the kind of weird quirk in counting up significant figures. You got to know where to stop. If you're dealing with a whole number, it's clear where to stop for the most part. There's a little quirk in that too. But for the most part, you stop at the end of the number, and 99% of the time it's really clear where to stop. It's that other 1% that gets us a little bit confused. But if you have trailing zeros to the right of the decimal point, if you have something that ends in, let's say, 0.300 versus 0.3, those have different numbers of significant digits, and I'll show you why here in a moment. So let's work through some examples here and figure this out. So simple number like 8.27. Well, 8.27, we start counting from the left at the first non-zero digit, and we keep on counting until we hit the end of the number. We stop counting unless there are trailing zeros at the end of the number, past the decimal point. So here, this one's pretty straightforward. It's got 3 significant figures. The 8 is significant, the 2 is significant, and the 7 is significant. So 3 sig figs. Notice that counting up significant figures never mentions exactly where the decimal point is, except for that whole trailing zero thing. So a number like 8.27 or 827 or 82.7, they all have 3 sig figs. Let's take a look at this one here, 0.00315. Well, follow the procedure. It says to start counting at the first non-zero digit. So those first 2 zeros, these first 2 zeros right here, are just placeholders. They're there to make sure that the 3, the 1, and the 5 are in the right places. So they don't really count. If zeros would disappear if you put the number into scientific notation, they're not significant. 3.15 times 10 to the negative third would be this number in scientific notation. And in fact, that's one way you can always go if you're not clear on whether or how many significant figures you've got. Put it in scientific notation. If you put the number in scientific notation, you'll be able to clearly see the number of sig figs. It gets rid of those leading zeros pretty easily. So we start counting at the 3. So we have no significant digits at those first 2 zeros. The 3 is the first significant figure, then the 1 and the 5, and then we hit the end of the number. So we've got 3 sig figs there. Something like that, 54971.3. Well, there, start counting at the first non-zero digit and count left to right till you run out of numbers. So we've got 1, 2, 3, 4, 5, 6. 6 sig figs there. Now, if we add a 0 on the end, by convention, this is something that people have decided on. This is something we've all agreed to follow. So it's a definition. It's not something that naturally would make sense. We had to define it to be this way. That adding a 0 on there tells you that digit is significant. When you put a 0 at the end of the number past the decimal point, it only counts past the decimal point. That 0 is significant. It's one of the only times that a 0 at the end of the number will be significant. I'll show you exactly why it makes sense to do this. But if we follow the rule here, just first to count up the number of sig figs, we'd start at the 5, start counting from the left, the first non-zero digit. We got 1, 2, 3, 4, 5, 6, and then we've got this 0 at the end. Trailing zeros after the decimal point count. So trailing zeros after the decimal count. So let's see why that is. So let's take our example here. We had 54971.3. What we're really looking at here is some sort of measurement. And we're comparing here the difference between 54971.3 and 0.30. Mathematically, there's no difference between these two numbers. They both have exactly the same value. The 0 doesn't add any additional value to the number, but it does tell us something. What it tells us is what the next division is on the tool that was used to make this measurement. Now, pretty clearly, I hope everyone would agree at this point, if I had had a number like 54971.34, you'd agree that that 4 is significant. Well, when you're making measurements, sometimes you end right at a 0. And that's what's happened here. The tool that we're using to make this measurement lined right up on 0 for that hundredths place. If we drop that 0, which we certainly can do mathematically, it's not going to make any difference in a calculation. Dropping that 0 tells us that the tool really can only measure up to the tenths place. I like to think of it kind of like a tape or a measuring tape or something like that. If I looked at the numbers next to the measurement I've got, the one below it would be 0.29, and the one above it would be 0.31 in the case where we have 30. In this other case, the one above it, the next digit up, where the next measurement up would be 0.4. And the next one down would be 0.2. You see the difference there? The what this is saying is that the tool on the left can only measure down to the tenths place. Its precision is only to the tenths place. The tool on the right, its precision is to the hundredths place. When you land on a zero on a more precise tool, if you drop the zeros, it makes it look like a less precise tool. So to recognize that we used a more precise tool and it just landed on zero, we write the zero, and we have to treat that zero as significant. And that's true for any kind of any number of zeros. For example, if like when I had you work with micrometers in the first semester and I had you measure gauge blocks, if I had you measure a 1-inch gauge block, you might measure that as 1.0000 inches. We'd write it like that because we actually did measure it down to the 10,000ths place. It just happened to come out to be 1 with a whole bunch of zeros after it. This would have 5 significant figures. The 1 is significant, and these zeros after the decimal point are significant. The next measurement up would be 1.0001. If we wrote it as just 1 with no zeros after the decimal point, then the next measurement up would be 2. So big difference there. So those trailing zeros are pretty important. So make sure you understand how and when to count those. So let's go back to our examples here. Try a couple more here. Whole numbers. Whole numbers can be problematic because it's not always clear whether these trailing zeros should count. Trailing zeros after a decimal point always count. They count as significant figures. By default, trailing zeros in whole numbers do not count. Essentially, the next figure up in this list would be 89500. We're dealing with some tool that can only measure in units of 100 or increments of 100. So this number has 3 sig figs. We have 8, 9, and 4. There's no decimal point involved, so these 2 zeros are really just placeholders. Zeros that are placeholders are not significant. That's why these 2 up here in 0.00315 were not significant. So 89400, that only has 3 sig figs. Now, sometimes, just like on the decimal side, sometimes you're using a tool that measures whole numbers and it lands on 0. We do need to have some way to indicate that we really have significant zeros there. Those zeros aren't just placeholders, that we actually measured those zeros. And there's a way to do that. The easiest way to do it, and the way I'd encourage you to do it if you ever get into this situation, is to write it in scientific notation. If you have 89400 and all 5 digits are intended to be significant, you'd write it in scientific notation. 8.9400. That'd be times 10 to the 4th. So that looks really sloppy there. So let me rewrite that. 8.9400 times 10 to the 4th. Now, because it's a number between 1 and 10, those 2 zeros became trailing zeros and they'd count, and we'd have 5 sig figs. But if those trailing zeros were not significant, you'd write it as 8.94 times 10 to the 4th. This one has 3 sig figs. This one has 5. Now, there's a shorthand way of doing that, and it's a little bit weird, and it's not something that we see very often because the situation doesn't come up very often. But one way to write it without having to put it in scientific notation is to throw a decimal point at the end. it's one of those weird situations where there's a decimal point, but there's not a zero afterward. So we've got 89400 with a decimal point on the end. That's meant to signal to you that those two zeros are significant. And we can't add another zero after the decimal point because that would tell us we're measuring down to the tenths place. This might be a tool that only measures down to ones, but is just landing on zero when we make that measurement. So if it gets to a point where you're trying to write down a number with a certain number of sig figs, or it would be unclear to write it down, throw it in scientific notation, and that usually resolves it. So how does this, so there we go, 8.94 times 10 to the fourth. So let's see how this could come up in a practical example. So let's say we got a very simple example here. We've measured the sides of this square to be 2.1 feet. So 2.1, we're using a tool that can only measure down to the 10th of a foot. And there are plenty of those out there. I have a tape measure that measures down to the 10th of a foot. It's a typical surveying kind of tape to measure down to a 10th of a foot. They usually go down to a 100th of a foot, but 10th of a foot we'll go with that on this one. So if I've measured the sides of this and found all four of them to be 2.1 feet, I've got a square, and I want to find the area. So we know how to calculate the area. We multiply the sides together. 2.1 times 2.1 gives us 4.41. Now our original measurement, we only had 2 sig figs. We had 2.1. Starting counting at the left at the 2, we've got 2 and a 1, that's 2 sig figs. But our calculated area has 3 sig figs in it now. We've magically created, or the mathematics has kind of magically created another figure. That overstates the precision of the tooling that we're using. We didn't use any tools that measured down to the hundredths place. We only used tools that measured down to the down to the tenths place. So that overstates the precision that we can know the answer to. So to avoid that overstatement, we round our answer down so that it matches the number of significant digits we started with. That's always the guideline. You look at the least precise bit of information you're using in your calculation. If that's 3 sig figs or that's 4 sig figs, that's the precision you'd be rounding your answer to. We always round our answers to the lowest precision that we've got. We do that at the end. We don't round in between as much as we can avoid it. We want to keep all those extra digits in our calculation, but when we go to present our final answer, we'd round that answer down to the correct number of sig figs. And that correct number of sig figs is the number of sig figs, the minimum number of sig figs, the smallest, in the input information you used. Now, in most of the problems we do, the numbers are to be considered exact. So if I write down the number 60, that's equivalent to 60.00000 going on for as many significant figures as you want, unless otherwise specified. So in those cases, it will always be made clear to you how many significant figures we need in our final answer. I might say, write your answers to 3 sig figs. Now that tells you something about how you can do your calculation. The general rule of thumb with rounding in the middle of a calculation is to keep 2 more sig figs than you need in the end. So if I need 3 sig figs in my final answer, I'm going to keep 5 in all the work I'm doing. That keeps all the round off error down in those digits that I'm going to get rid of. And it won't let that round off error affect my answer. So rounding is going to be pretty important, and rounding is can save us a lot of work. It's not a problem usually to have extra digits in your calculations. It just adds extra work for you if you're writing things down. But when you're presenting answers, you want to round to the correct number of sig figs. We want to keep enough digits to make sure we're not introducing error, but we don't want to keep so many digits that we're spending all our time writing down these big long numbers. So remember the basic rule for rounding here. You figure out where you're going to round it, and you look at the first digit that you're going to drop. If the first digit is 5 or greater, add the last digit you're keeping, add 1 to the last digit you're keeping. If the first digit you're going to drop is less than 5, just drop it, and nothing needs to be done. Nothing else needs to be done. So let's put rounding and sig figs together here and go through some examples. And if you're watching this on the video, once I've got these all listed, you can kind of pause it and check your answers, work it out yourself, and then check your answers. So here, the problem is asking us to round each of the following so they have 3 significant digits or 3 significant figures. So in order to figure out how to round them so they have 3 sig figs, we've got to count up to that third sig fig. That third sig fig is the one we're going to keep. So we start from the left. The 3 is the first sig fig, 1 is the second, 4 is the third. So right there, in between the 4 and the second one, is where we're going to round. The first digit we're looking at throwing away is just a 1, so we drop it. So in this case, let's see here if I can, nope, I guess I can't. So in this case, we'd write our answer as 3.14. So our answer there would be 3.14, 3 sig figs. We try a number like 2.71828. Start from the left. 2 is the first sig fig, 7 is the second, 1 is the third. So we're going to round right in between that 1 and that 8. First digit we're throwing away here is an 8. So that's greater than 5. Well, 5 or greater, I suppose. So we have to add 1 to the last digit we're keeping. So properly rounded to 3 sig figs, this would be 2.72. And I'll put all the answers up on the screen when we're done with the example. So we've got 3.14 and we've got 2.72. So those were pretty straightforward ones. Let's go to something a little more challenging. Here we want to keep 3 sig figs. And we've got a whole number. So we'd round based on that third sig fig, we'd start counting to the left, from the left, 8, 7, and 2. So our 2 is our third sig fig. We're going to round right here in between the 2 and the 0. Well, the 0 is the first digit we're throwing away. That's less than 5, so we just throw it away. We'd have to write this one as 87200. In whole numbers, you've got to add enough zeros to keep your significant digits in the right place, or write it in scientific notation. Either way would work. If you wrote it in scientific notation, you'd write it as 8.72 times 10 to the 4th. So let's look at that on the display here. 87200 would be correct for rounding to 3 sig figs, because remember the rules for sig figs and whole numbers. You start counting from the left, stop at the we'd stop at the 2. These trailing zeros in a whole number don't count unless there's a decimal point there. So this only has 3 sig figs. It's a little clearer in scientific notation because we can drop those placeholder zeros and just write it as 8.72 times 10 to the 4th. Let's try another one here. There's another whole number. So 12375. We'd start counting from the left. 1, 2, 3. In between the 3 and the 7. The 7 is greater than 5, so we'd add 1. So that would be 124. And then we have to add those 2 zeros in to make sure the 1, the 2, and the 4 are in the right place. So we'd have 12400. Still has 3 sig figs. And again, if it's unclear, write it in scientific notation. 1.24 times 10 to the 4th. Let's try a small number here. Here's where where rounding by sig fig versus just rounding by decimal place is beneficial. Sometimes you deal with small numbers. If you just round by decimal place, if I just rounded to the third decimal point or decimal place, I'd be losing a lot of information. We start counting at the first non-zero digit. So these first few zeros don't count. Our first significant digit is the 3. So we have 1, 2, 3. We're rounding in between the 1 and the 9. The 9 bigger than 5, so we'll add 1. This would be 0.00372. So leading zeros, those don't count. That makes sure that even if we're dealing with a really, really tiny number, we can still round it and keep some information. If we just rounded by decimal place, if we had a really small number, we could round the whole number off and just call it 0. And that might be an unreasonable thing to do. And then last one here is a little bit of a challenge, because this one we'd have an issue writing this to 3 sig figs. So let's try that one out. I'm going to write that one down, and we'll go over to the camera on that. So 380019. It's a whole number, and we want to round this to 3 sig figs. So we can count here. We've got 1, 2. Now zeros in the middle are considered significant, since it's pretty clear here. The next increment up would be 380020. So we're definitely using a tool that can measure down to 1. So we'd start counting here 1, 2, 3. So we'd round right there. Since the first digit we're throwing away is a 0, we're just going to throw the whole thing away. But in a whole number, remember, you've got to pad out the placeholder zeros so that it stays a whole number. This thing was around 380,000 before we rounded. It can't be 380 when we're done rounding. Rounding can't change the value by that much. Rounding is meant to be a small change. So rounded, we run into a problem here, because if I write it as that, it looks like it only has 2 sig figs. Because remember, these trailing zeros on a whole number by default don't count. So I've got 1, 2, and I'm not sure about the rest of the zeros. But if I put a decimal point here, now all 6 of them are significant. This number, you cannot actually write this rounded to 3 sig figs unless you put it in scientific notation. So the only way to write this number 380019 rounded to 3 sig figs in scientific notation and have it be absolutely clear it's 3 sig figs is to write it as 3.80 times 10 to the 5th. 3.80 times 10 to the 5th. Now 3.80, that's pretty clearly 3 sig figs. We got 1, 2, and trailing zeros count after the decimal point. So scientific notation can really help you out there in situations where rounding makes things ambiguous as to how many sig figs there are. All right, any questions so far? I know it's a lot of stuff, but it's most of it is review. We've just got one little bit to take a look at here and finish up with tonight, and we'll be done for the evening. So let's take a little look at algebra. So algebra, this part of algebra is something you should be familiar with. If you did okay in weight and balance and all of that, you shouldn't have any problem solving realistic equations. The only thing we're really taking away in this class from the algebra section that you may have done in other courses or other classes is just the ability to solve equations. So as long as you're feeling comfortable solving an equation, if I write an equation like 3x plus 5 equals 9, you can figure out what x is, you're in pretty good shape. We're not dealing with lots of crazy algebraic expressions multiplying 3x squared plus 5x times 10a plus 2b. We're not doing that kind of those kinds of things. Those aren't realistic for our purposes, and we don't need that in any part of this class. So we're not going to bring those tools in, but you absolutely need to be able to solve equations. So while algebra can involve a lot, we're not going to be using a lot of that power. Uh, in algebra, we do let symbols and letters stand in for unknown quantities, and we use the rules of mathematics to solve for unknown values. That's the real power of algebra, and that's what we really need to be able to solve for unknowns, because in certain situations, we may be able to make lots of measurements, but we may not be able to measure exactly what we want to know. But if we know enough about other parts, and we know how the system is supposed to behave, we can put all that together into an equation, what we call an equation of equilibrium. And that equation will let us figure out what our unknown quantity is. So we can get new information we weren't able to measure by solving equations. And for our purposes, at least today, we're only going to deal with one unknown quantity. And this is what we did in solving equations in the A&P program. Every equation you solved in the A&P program only had one unknown quantity. You needed to find the amount of weight to add at a particular location, or where to add 10 pounds to bring the CG to the right location, or to solve for the center of gravity. There was only ever one piece missing. And that's what we're going to review on here. Next time, we're going to bring in two unknowns, because in principle, we can end up in situations where we have two unknown quantities, and we have two equations that those unknown quantities have to work in. That's not something that we've practiced before, at least not in this class. It's about the only piece that we're missing. So we'll be spending a fair bit of time next time figuring out how to deal with two unknowns. But one unknown we'll be able to we have that background here. So let's practice on it a little bit. So let me review with you the procedure for solving equations. So we'll go over to the camera here. I'll copy down the equation 3x plus 5x equals 8. So the basic procedure has been to first simplify things down. So remember, simplification means combining like terms. So if you've got two quantities that have the same symbol, or you've got numbers, you can add those together. You can combine them. So the first step in solving an equation, so solving equations, step one, simplify both sides. By combining like terms. So we simplify both sides by combining like terms. So on the right-hand side here, we've just got 8. We can't really do a whole heck of a lot with that. Over here, we've got 3x and 5x. Well, those both have the same symbol, x. And in the practical equations that we deal with, you're always going to have 2 or fewer different symbols. None of this 10x squared plus 4a squared b cubed plus 5y to the fifth. There's none of that craziness. That's not anything we need to deal with physically. The most you can have is 2 unknown symbols in a term, or on a side of an equation. And if we're only dealing with one equation, we can only deal with one unknown. So all the symbols would have to be the same. So here we have 3x plus 5x, that'd be 8x. Remember that when you simplify, you combine like terms by adding the coefficients and keeping the symbol the same. So we're keeping the x, but we've got 3x's from one and 5x's from another. That's a total of 8. So 8x equals 8. So we simplify both sides down. The next step would be to get all the symbols on one side and all the numbers on the other. Now, we don't have to do that here because this was a relatively simple equation, but we'd use addition and subtraction to get all the symbols on one side and all the numbers on the other. Well, that's already done for us here. We'll do another example where that isn't done. Third step is to essentially make the coefficient of the unknown 1. And in most every practical purpose, we do this by division. So remember what this says here is this is saying 8 times x. Well, we want to get rid of that 8, just like we got rid of feet in our unit conversion. If you've got something in the top you don't want, put something in the bottom that's the same so that they cancel out. But the cardinal rule with equations is whatever you do to one side, you've got to do to the other. You got to keep the scales balanced. So whatever we do to one side, we've got to do exactly the same thing to the other. So if we divide the left side by 8 to get rid of that 8 in front of the x, we also have to divide the right side by 8. Division is always your last step. Division is always going to be your last step to getting your final answer. So I'll write this specifically for what we'll be doing. Divide out the coefficient of the unknown. So that means divide both sides. That'll make the coefficient of our unknown 1, since 8 divided by 8 is just 1. And on the right side, we get whatever that simplifies to. So x equals 1. Now, I encouraged you in the first semester to check your results by plugging this back in. 3 times 1 is 3, plus 5 times 1 is 5, 3 plus 5 is 8. It checks out. The practical matter is in real work, almost no one does that by hand, because we don't usually have nice simple equations where we get 1 as the answer or 3 as the answer. We get 0.57743 as our answer. And now we have to go figure out, does that work? Where we use that, it is something that's used, but we use it in a computer program. If we have some sort of solver that is doing the work for us, in the end, one of the things that program would do is take the answer and plug it back into the original problem and make sure it works. In fact, some systems are completely built around just doing that. That's how they solve it. They take the answer they've got, they plug it in and see if it works. If it doesn't, they make an adjustment to the answer, try another guess, and just by trial and error, loop over the solution until you get the right value. We don't have to do that, but in a practical sense, it becomes kind of difficult to actually do these checks. So instead, we rely more on intuition and on making sure that our answers are reasonable. So that's our basic procedure for solving equations. So let's try another example here. So there's one that's got a little bit more to it. We've got 2x equals 10x minus 16. So let's try that one out. So we'll follow the same procedure here. We'll simplify both sides down. Well, there's really not a whole heck of a lot to simplify there. 2x can't be combined with anything. We can't combine the 10x and the 16 because 16 is a number. 10x has an x in it. They're not like terms. So we're done with step 1. Step 2 we'd use addition and subtraction to get all the symbols on one side and all the numbers on the other. Now, it's a judgment call for the most part about what side to use for symbols or what side to use for numbers. A lot of times you can kind of look ahead a little bit and try to figure out what's going to set me up for the best situation later on, especially if you don't like dealing with negative numbers. But there's also an aspect of doing things in the fewest number of steps. In this problem, I've got x's all alone already on the left. So that would seem to be a natural place to put the x's. On the right, I've got numbers here. If I can get rid of this 10x in one step, I'll have satisfied step 2 and gotten all the symbols on one side and all the numbers on the other. So here I'd use subtraction. I've got 10x, that's a positive 10x. So I'd subtract it. But remember the cardinal rule here for solving equations. Whatever you do to one side, you've got to do to the other. So if I subtract 10x from the right, I've got to subtract 10x from the left also. And be careful here. This is where I see people make a lot of mistakes, is in combining these. 10x minus 10x is 0. So those two obliterate each other. And we're just left with this negative 16 on the left, on the right. Here we've got a positive 2x minus 10x. So watch your signs. We keep the x. We've got 2 minus 10. That's a negative 8. If you struggle with that a little bit, make sure you review on adding and subtracting signed numbers and things like that until that's a little more comfortable for you. But negative 8x equals negative 16. We've got all the symbols on the left, all the numbers on the right, so we're done with step 2. To finish up, we divide out the coefficient, and that includes the sign. So be careful to divide by negative 8x, not 8x, or by negative 8, not just 8. If you only divide by 8, you'll have a negative x. That's not what we want. We want x equals some number, positive 1 out in front. So if I divide the left side by negative 8, I've got to divide the right side by negative 8. And here I've got negative divided by negative, so it's positive. 16 divided by 8 is a positive 2. And that'd work if I go and check that. 20 minus 6, 16 is 4. 2 times 2 is 4. So it checks. And then we've just got, I think we'll just do one more example. And that one more example here should have, well, let's do, actually none of these are particularly challenging as far as that goes. These are all pretty much the same as the other ones we solved, so you can check those out on your own. About the most complex situation we could ever possibly come up against would be if we had something that looks sort of like this. So let me try to keep the procedure on the paper. There we go. So let's try something like 3x minus 10 equals 8x plus 5. Let's say that's what we get after we've simplified everything down. So we've simplified everything down. The most we'll ever get on each side is 2 terms because we've got unknowns and numbers. We can never reduce it any further than that unless there are only symbols or only numbers. The issue here that makes it different from the other examples that we've done is that we'd have to make a call as to which side we use for symbols and which side we use for numbers. And there's no way to get around doing 2 operations. We're going to have to add or subtract once and then add or subtract again because we've got numbers in the wrong places. We've got symbols in the wrong places. If the left is our symbol side, then the 10's in the wrong place, and so is that 8. x. So we're going to have to move both of those. This is about the most complex as far as a single equation goes that we'll ever see in this class. The only thing that makes our problems a little more challenging is that these coefficients are not numbers, not whole numbers like this. They'll be decimal numbers. Typically, they're sines and cosines of angles. So, but the skill is the same. So let's go ahead and let's pick the right-hand side here to be our symbol side. I usually pick the one that's got the bigger positive coefficient. That way, I avoid dividing by a negative number later on. And I think a lot of people do that. So if that's something that's in your habit, I'd keep doing that. So I'm going to pick the right hand side to be my symbol side. That means this 3x is in the wrong place, so I'll subtract it. Since it's added in, it's got a positive out in front of it. So I'm going to subtract 3x from both sides. 3x minus 3x, those two obliterate each other, and I'm just left with negative 10. On the right, I've got 8x minus 3x. That's positive 5x. And then I've got plus 5. So notice we didn't get down to all the symbols on one side, all the numbers on the other. We did get all the symbols on one side, but all the numbers aren't on the other. So we need to do another step, and that means subtracting this 5 from both sides. Now the 5s cancel each other out there. 5 plus a negative 5 is 0. So all I'm left with is 5x on the right. Negative 10 minus 5, that's a negative 15. So now we've satisfied step 2. At most, it should only take you 2 steps to satisfy step 2. One's going to involve getting all the symbols on one side. One's going to involve getting the numbers on one side. If you're lucky, all the symbols are already on one side, or all the numbers are already on the other, and you only have to do one operation. But once we're into step 3 here, that's our divide step. So we divide both sides by 5, and x would be negative 3. So there we go. That's about the most complicated, at least structurally, a single equation can get. Anyone have any questions so far? All right. Well, let's see here. Let's go back to the notes. So you can try out the other ones if you're feeling a little bit uneasy about your algebra skills. Try the others out, and if you're not sure, if your answer doesn't check out or things are not working, take a picture of your work, send it to me, and I'll see if I can debug it. So next time we're going to work on what we call simultaneous equations. Simultaneous equations are 2 equations, for our purposes, 2 equations and 2 unknowns. So where we have 2 equations, both missing 2 pieces. If we put them together in the right way, we can figure out both of the missing pieces. So that's what simultaneous equations are all about. And if you've dealt with them before, you may know various methods of solving simultaneous equations. I'll show you a few different methods next time. And if you know things like Kramer's rule and all that, that may be something that'll be useful to you. Or if you know how to make your calculator do it, there's always that. But simultaneous equations, probably something you're not as familiar with. So we'll spend some time on that. And then we'll be reviewing a little bit of trig. Trig's the last mathematical piece we need to be able to solve practical problems. In fact, next Monday night, we'll be starting into equilibrium problems. We'll be working with forces and doing solutions of equilibrium problems. So we've got to review a little bit of trig. So we'll go over sine, cosine, tangent, the ratios, and how we use them to break apart a triangle, find the legs when we know the hypotenuse, and go backward, find the hypotenuse when we know the legs. I will also be handing out or issuing on the website homework 1. In fact, sometime either Tuesday night or Wednesday morning, I'll be posting the notes and the homework assignment on the website, so you can get a look at those early if you're interested in doing so there. Let's see here. And there we go. Anyone have any questions?
Nope.
All
I
right.
don't.
Well, hopefully it was all mostly review for everyone, but practice it, go back over some of the stuff if you're not comfortable, and if you've got any problems, questions, feel free to let me know.
All right.
All right. Then have a good evening, gentlemen.
Yep, you
You
too.
too.
Have a good one.
Have a good night.
Good night.